Yes, power and energy. I'm full of the dark side today. I'm very excited about this. Before we get in power and energy, let's talk about time. It's always in seconds in physics. But in the outside world, very often it's in hours. That makes sense. Do you want to get paid in dollars per second or dollars per hour? And for the watt, it's kind of a small unit. So you wouldn't want to measure the distance to Toronto in meters, so we don't generally measure watts. We measure kilowatts and megawatts on the industrial or household scale. So get used to that. We already looked at energy is force times distance, which is a Newton meter giving us the joule. So we could say my car dissipated 1 megajoule of energy. All power does is take that amount of energy and considers the time in which it took place. So how many joules per second? And we've nicknamed the joule per second a watt. So for example, my car dissipated 1 megajoules in 15 seconds. Divide these two numbers and we get 100,000 joules per second, which is a watt. Always convert W to J over S, joules per second, and you will not make any mistakes. What formulas does energy over time apply to? Any of the formulas we studied. All the mechanical formulas are based on force times distance, and we looked at general acceleration, falling or rising in a gravitational field, dragging something on a surface with friction, pulling back a spring until you put someone's eye out, and fast as a speeding bullet. We also did some heat equations, but we don't have to worry about that. Any of these works and energies divided by time will provide you a power level in watts. Let's take our traditional elevator problem. You have an elevator going up 100 meters, 2,000 kilograms. There's the formula calculating the joules of energy that will be expended lifting these two elevators to the top. But there's a time difference here. The first elevator needs the 2 megajoules of energy delivered in 10 seconds, which means 200,000 joules per second is what will be needed to power the elevator. The second one, the 2 megajoules only needs to be expended in 45 seconds, so you get 44,000 joules per second. This would give you an idea of the size of motor you needed. The small elevator needs a 44 kilowatt motor, and the big elevator, the faster one, would need the 200 kilowatt motor. And this answers the mystery, why do short buildings have the crappiest, slowest elevators? Because the faster you want the elevator to go, the more you're going to spend on that motor. So it's easier for a small building that has a lower budget to use a slower elevator. The other reason we want to look at power is very often the energy we're going to expend is delivered to us over time. So let's say I have 10,000 joules stored in this battery, and the joules drain out at 50 joules a second, 50 watts. It makes pretty good sense that this will take 200 seconds to drain. I could turn this to 10,000 liters of water, and it's leaking at 50 liters per second. It's pretty obvious what you should be able to do. Many things we look at are a flow rate. We already know how they're coming in. Electricity, water, natural gas. It's also true of UL. You might be able to lift 50 bricks onto a pickup truck, but can you do it in 20 seconds? So an older man and a younger man may get the same job accomplished, but one of them accomplishes it slower. The power output is dropping, but the total energy may be the same. Very often we're asked to report energy totals from the power itself. That's like saying, hey, I'm paying you $200 a day versus I'll pay you $20 an hour for 10 hours. Those are the same numbers. Just one was phrased from a flow rate and the time, where the other one reported a total. I could say this tank is leaking at 50 liters a second for 100 seconds. How much is that? That's going to be 5,000 liters. That would give me two choices. I could say, I want you to get me 5,000 liters of water, or I could say, turn this valve on to full and do it for 100 seconds. That is 5,000 liters, just phrased oddly. What about a 1,000-watt light bulb turned on for 2 hours? This is 1,000 joules a second for 7,200 seconds. So it's 7,200,000 joules. But it turns out for electricity usage, we usually just leave the 1,000 alone, leave the hours alone, and say 2,000 watt hours, which is 2 kilowatt hours. This is a rate phrased off duration. This is saying I want you to turn on a 2,000 watt light bulb for 1 hour. That is a total. It's just phrased really odd. That would be like saying, turn the dial up here so this liquid is coming out 2,000 liters a second. Please leave it on for an hour. So kilowatt hours is a total. And this is one way of looking at it. 60 watts means 60 joules per second. If 60 joules per second are coming down the pipe, how much has filled this container? Well, you'd take the 60 and multiply it by the time. This would work if it was liquid. 60 liters per second times the time will give you the total. So these are the two most common ways you'll use the power equation. At home, if you turn on a 100-watt light bulb for 10 seconds, the total energy consumed is 1,000 joules. There's a bit of an odd thing, though, in electricity. We see power a lot, but we also see amps. Both of these are rate, but power is an energy rate, joules per second, which is called a watt. Current is a quantity rate, how many electrons per second are passing by. So a coulomb of electrons is like a cup of water. It's a huge bundle of molecules. When you say there's a 3 amp circuit, you're saying 3 cups of electrons per second are coming down the circuit, but you know nothing of those electrons. You don't know whether they're highly energetic or low energy. Think of a cliff. If someone's pitching 5 rocks a second off a cliff top, until you know the height of the cliff, you don't know how hard those rocks are going to hurt when they hit you. So these two terms are used interchangeably a lot in physics, but there's a very specific meaning difference. Cups of electrons per second, joules of electrons per second. An amp hour would be the equivalent of me saying 5 cookies per second for 2 hours. You can work out a total in cookies. But what are they, marshmallow cookies or are they rice cakes? A watt hour would be like saying I ate 5 100-calorie cookies per second for 2 hours. This is actually energy now, or calories. Calories and joules are pretty much the same idea. If you leave a 5 amp circuit on for 10 hours, you get 50 amp hours of electricity. But you don't know the energy in those electrons. But the same 50 amp hours, if you said they are 120 volt electrons, then this means there's 6,000 watt hours. A volt is like a meter in a sense. So if I say to you this is a 1 volt rock, it means you're dropping it from 1 meter. If I say it's a 100 volt rock, that means you're dropping it from 100 meters. So when we apply the current and the voltage together, we can calculate the power in an electric circuit. There are voltmeters, there are amp meters, there are no joulometers, and there are no joulometer per second devices. We easily can measure current and voltage on a circuit and calculate the power. You want the time, just pay attention to your watch and time the event and multiply it, and you got your energy.